Good morning, dear students. Welcome to this interesting session on orbital velocity. So, today we are going to derive an important expression for the orbital velocity, which is very, very important uh, when a celestial body, or in fact, any small planets which is revolving around bigger planets, how they are experiencing the speed in a specified orbital path or in an orbit. That is called as the orbital velocity. So this is very, very handy. So now, without wasting much time, we'll get back to this equation and how it is going to derive, and how this method is very, very different from all other textbook. Okay, so in different textbook, they have gone to a different concept, and they have explained it very well. But today we are going to see some of the possibility where this derivation will make you a good uh, or give you some better insight comparatively with the books which you have referred. Okay, so today I am going to introduce good methods how you are going to physically you're converting a quantity into a mathematical expressions. Okay, so we are going to do that now. So now let's consider a body of mass of m. Okay, now let's say we have a very small mass, we call it as a point mass. I'll write here point mass. Okay, now I write something called the point mass. So, and we have a very big mass here. This is a planet. So I denote here it as an m, here denote it as a big M. Okay, now let us consider it's orbiting in a circular path, which is normally the path can be even circular or elliptical, but for the simplicity we always go with the circular path. Okay, so depending upon the mission complexity, so here we'll try to assume that this mission is very simple, because we consider only a revolving mass around a bigger mass of m. So here we consider the path as a circular path, so which has been very clear. So now let's take the center of this mass. Now this is our earth. Okay, this is our earth. We take this as a reference. This is our earth. Now if you see, I draw a line over here. Now this is actually the radius of the earth. Okay, now this is being separated with some distance, and we need to find out the total distance. Okay, so I'll draw the diagram like this here. Okay, so we have RE, and here you have a mass of m, so this is m. And now uh, the total distance will be RE plus h. Okay, and let's say we have some small height which has been coming, which is separated with the height of h. Okay, up to the surface, this point to this point. So the total height should be equal to the total distance, that should be equal to RE plus h, including this radius of the earth. So as we know that this small mass is being rotating around the bigger mass. So now let's say this is a celestial body. This is going to rotate, or it can be a satellite. This is going to rotate uh, within the Earth gravitational pull. So here we experience the Earth gravitational pull, and to a certain specified orbit, if it is rotating, then probably it experiences a force which is called as the centripetal force. So centripetal force is nothing but the force which is experienced by any rotating body which is pointing towards the center of any bigger mass. So this mass of the earth is the center of the earth is the center point where it attracts the smaller bodies towards it. So that is called as the centripetal force, which is being experienced by the smaller mass, which is denoted by m into a suffix c, where AC is the centripetal acceleration. Centripetal acceleration. and Fc is the centripetal force. So this is having a unit of meter per second square. We'll take this as an SI units. This can be newtons. Okay, fine. Now we need to quantify the centripetal acceleration. Okay, so we don't go with the complex terms, but we'll try to understand whenever a body is being rotating, it is always having a velocity of v. Okay, now I'll write over here as well. Now it is rotating with a velocity of v. Okay, it is rotating with the velocity of v, and now we can say that the total distance being covered, okay, by this object of mass, that is actually re plus h. Okay, so the acceleration at every point in the orbit should be a function of the orbital speed. Let's say it is a VO orbital, VOR something, VOR. And this acceleration is a function of V orbital and the radius of the earth plus height, that is the total height from the above the earth's surface. Now this is been rotating just like a ball which is being tied to a fixed point. Okay, if this is a ball, you are trying to rotate it, so the same phenomena is happening over here. Okay, you have a fixed point and now this mass is going to rotate like this, maybe at a distance of re plus h, and now we have a mass m here, and the orbiting velocity is basically called the orbital speed, that is called the VOR. So from this figure itself we can tell, okay, we have a centripetal acceleration, anyway centripetal force is there, so the associated acceleration term will be centripetal acceleration. So this acceleration quantity is, we can tell it is a function of your orbital speed and as well as the total distance. Okay, now if you see a concept called the, or recall a concept called the dimensional analysis. Okay, dimensional analysis. Okay, you know the physical meaning or the physical relationship between different parameters, but you are not able to find out a mathematical relationship, then probably the important and the most powerful tool that we normally use is the dimensional analysis. Okay, which tells me that, so we have a function term, so we need to remove this function term. So basically what we do is like we introduce a constant, because we don't know the units, what type of units that this acceleration gonna take, but we know it is actually a centripetal acceleration. So we can have k value here, and now we denote the orbital speed as a raised to the power of a, and you denote re plus h to the power of b. So this is called the principle of homogeneity, which you have already studied, and this is also called the dimensional consistency. Okay, which you have already learned in your elementary high school. So in order to make, or in order to find out a good expression for AC, we introduce a constant k, because we don't know the what is the dimension it is going to take. Okay, so any quantity, if you are removing a function sign, we introduce a constant term. Whenever we do the dimension analysis, we introduce a constant term, and we introduce some exponents raised to the power of the physical quantities. So these are some of the physical quantities, and we raised some arbitrary constants, which is a, b, and if you have multiple uh, parameters, again it will be going with a, that parameter raised to the power of c, d, then it keep going. So here we have two parameters, so let's say a and b, vo to the power of a, re plus h to the power of b. Okay, now I think this is very clear. Okay, so the basic idea is, if a is a quantity, then probably if it is a function of a different different quantity, then probably A can be written as some constant, maybe lambda or something, into b to the power of a, small a, c to the power of small b, d to the power of small c, then e to the power of small d, and it's keep going. Okay, the same thing was already introduced here. Okay, now I won't repeat it again, but I think this has been very clear. Okay, I feel some concepts I may repeat because I feel that needs some repetition. So that is why I keep repeating some concepts so that it will inject into your brain so you can use it somewhere, which is very useful. Fine. So we have AC here. So AC term. So when we recall, if you are writing a dimensions for any quantity, we express in terms of mass, length, and time. So in your basic, your 10th or 12th, you have studied AC is basically like LT to the power of -2. Okay, K is actually a constant. I don't know what is K. So V orbital is nothing but the velocity again, which we have already seen. The velocity units will be meters per seconds. Now when it comes to dimensional sort of thing, you write your velocity as L by T, distance or displacement upon T, divided by T into A, okay, into Re plus H. So this is basically the length parameter. Now we raise to the power of b. Okay, now we equate only the variable terms because k anyway it is not there, because it's when we equate the exponentials we don't find any relevancy for k here. Okay, fine. Now we group the term lt power -2, which is equal to k into l raised to a. This is a bit tricky again, you need to be very careful. Okay, L raised to a, fine, you have b here, so into b, now you have t divided by t is t power -1, so it should be -1 to the power of a. Okay, now lt -2 should be equal to k a into l raised to a plus b, t power minus a. Now you can write L into, now you equate the constants, sorry, the exponents with respect to the LHS side. So you have L should be equal to L power a plus b. That implies a plus b should be equal to 1. Now you have, okay, so again t power minus a, that should be equal to t power -2. That implies your a power is 2. Okay, so from these two equations we can tell you have a term, you have b, so basically b will be -1. It's just a simple math, so b equal to -1. So that means ultimately you're going to get acceleration is equal to k into, what is the power of v? It's nothing but the 2 and re plus h. It's very simple, you have, it's -1, so you can write AC is equal to k v square divided by re plus h. It's very simple. Now you introduce a concept of unit balance. Okay, you need to balance the units of LHS and RHS. Now you balance the units meters per second square. That should be equal to k into meter square plus per second square divided by meters. Now meters get cancelled off, you get meters per second square. Meters per second square, you end up with k equal to 1. So finally you are going to get AC is equal to v square divided by re plus h. So this is a very important relationship. Okay, now get back to this figure again. Now you have the two terms here, you have the mass, you have m. So this mass is going to exhibit some sort of a gravitational force to this smaller mass. So obviously you're going to get a gravitational force which is denoted by gmm divided by r square. As this mass is going to exert a gravitational force on m, so probably you may get a negative sign here. Okay, so this mass is going to be very small, so this is to be a decreasing quantity. Now again, F is equal to a m times AC, which you have already see here. This is AC. Now we try to uh, substitute the new AC value, that is v square by Re plus h. Now this will be turning into mv square divided by Re plus h. Okay, here you need to be very careful. This R should be the total distance, that is Re plus h. So it should be Re plus h whole square. Okay, now you balance the two forces, Fg plus F, that should be equal to 0 for a total uh, conservation of force or conservation of momentum or energy. So when energy is concerned, probably the force should be also be conserved. Okay, because we have already seen force is a gradient of energy. Okay, so here if energy is conserved, then probably force need to be conserved for the total system. Okay, summation of F, this is the equilibrium of forces, should be equal to 0. Okay, that means mv square divided by Re plus h, that should be equal to gmm by Re plus h the whole square. Now you cancel the 1 Re plus h here, and again you remaining with 1 Re plus h over here. So you get mv square should be equal to gmm by Re plus h, and now your m get cancelled off. You end up with v square is equal to gm by Re plus h. Okay, now you take only the positive values, so you have square, it should be a plus or minus of g by Re plus h, but normally we go with the positive value because I don't want my orbital speed should be decreased. Okay, it should continuously revolve happily, so we go with v is equal to root of gm by Re plus h. Now I make a small approximation here. Okay, so this is a very handy equation when any satellite is being placed above the Earth's surface, then we have to take the consideration of the height. So we'll just simplify this equation for the time being. So v can be taken as root of gm by Re into 1 plus h by Re. You agree with my point? Yeah, you have something like this. So gm, we know it is a gravitational parameter represented by mu, and this is Re, so we can write v is equal to root of mu divided by Re, okay, into 1 plus h by Re. Okay, now let's see that your h is going to be, now in this figure, now h is very small. Now let's say this is being so close to the surface. Now h is very small, so this equation, your very smaller quantity divided by a bigger quantity, because Re is always having a approximately, okay, approximately this is the radius of the earth. Okay, so this is 10 power 6, maybe this is up to 100 meters or something, then probably this is going to be a very low quantity. So your v should be equal to root of mu by Re, because this gentleman, this total term should be going to be neglected because h is very small, Re should be very big. So a small quantity by a bigger quantity result into a much more smaller quantity. So 1 plus a smaller quantity should yield to me 1. So your mu by Re plays the overall value. Okay, so this is the expression for orbital speed. So normally for Earth we have the radius of the Earth mu, gravitational parameter, which is again a product of uh, gravitational constant into mass of the Earth, okay, divided by Re. So this tends to be almost 7.919 or something kilometers per seconds. Okay, now this is the expression for the orbital speed, which is given by root of mu divided by Re. So here we haven't gone with any fundamental vector uh, formulation of your velocity terms or any other stuff. Just we have done some dimension analysis, because by seeing itself we know that okay, there is some centripetal force is being experienced by any rotating or a revolving body. So accordingly we got the feel how the physical quantities are associated and how these physical quantities can be converted into mathematical quantities. So this much a very good work we have done here. And we also see for any satellite, if you are placing it to an height above the Earth's surface, then probably we are able to calculate its orbital speed as well. Okay, so this is one of the important relation in relation with the height. And when height is very very small, your orbital speed is equal to mu by Re, so which is again an important expression. So we'll wind up here and hope you have enjoyed this video. And for more videos you can visit to my channel, and whatever concepts you require me to make it very simpler, please let me know so that we can learn together. Okay,